Welcome to Talk Tensors. Today we're diving deep into a really interesting paper. It's called FedJoint, Joint Modeling of Nonlinear Degradation Signals and Failure Events for Remaining Useful Life Prediction using Federated Learning. Quite a mouthful, but important stuff.
It really is, because this paper, it gets right to the heart of a major challenge in practical machine learning today. How do we build good predictive models when the data we need is scattered all over the place?
Right, like in different factories, maybe different companies even.
Exactly. Think aerospace, manufacturing. The data that could predict when a machine might fail, it's often locked down. Privacy reasons, ownership issues, sometimes just the logistics of moving massive data sets. So this paper, FedJoint, it offers a way to learn from all that distributed data without actually, centralizing it.
Yeah, so the core problem is predicting remaining useful life RUL. Super important, right?
Absolutely. Better RUL means smarter maintenance, less surprise downtime.
Saves money, basically. But the data you need, sensor readings, vibration, temperature, all that, it's stuck in these silos. And trying to pull it all together, that causes headaches, privacy, IP, just the sheer hassle. And crucially, the way things break down in the real world. It's often not neat and tidy. It's nonlinear.
Precisely. And that's where FedJoint steps in. It's a new federated learning framework.
Okay, so maybe a quick refresher on federated learning.
Sure. So federated learning lets you train an ML model across loads of different devices or servers wherever the data lives locally. But the clever bit is you never actually move or share the raw data itself.
Ah, right.
Instead, each location, each site trains a model on its own data. Then only the model parameters, kind of the distilled insights or learnings, get shared and combined to build a better global model.
Privacy-preserving learning.
Exactly. So FedJoint uses this approach to model both those complex nonlinear degradation signals and predict the actual failure event, the time to failure. It does this jointly.
Jointly meaning it considers both things together rather than separately.
Yes, precisely. Because how something degrades is directly linked to when it's likely to fail. It's a collaborative way to learn without the data sharing nightmare. A real step forward for using distributed data.
Okay. Let's dig into their method. How do they model those messy degradation patterns? The unpredictable wear and tear.
They use something called a federated multi-output Gaussian process, an MGP.
Gaussian processes. Okay, those are powerful but can be complex. What's the key benefit here?
Well, they're non-parametric.
Meaning
the model doesn't assume a specific mathematical shape for the degradation beforehand. Like, it doesn't force the data into looking like a straight line or a specific curve.
Oh, okay. So it's more flexible. It learns the shape from the data itself.
Exactly. Think of it like modeling clay versus a fixed mold. The GP can adapt to whatever complex, wiggly pattern the real data shows.
And multi-output.
That just means it can handle signals from multiple sensors at the same time, temperature, pressure, vibration, whatever, to get a more complete picture of the machine's health.
Okay, and how does the federated part work with the MGP? How do they share insights without sharing data?
Good question. They use a technique involving inducing points. You can think of these as, like, virtual summary points or representatives of the local data. These inducing points allow the models at different sites to sort of coordinate and estimate correlations between different machines' degradation patterns, but without needing the raw sensor readings from each one. It's quite clever.
I see. So that's the degradation modeling part. What about predicting the actual failure time?
Right. For that, they use the second piece, a federated Cox proportional hazards model. Cox-PH.
Cox models. I know those from survival analysis, like in medical research.
Exactly the same principle. It's a standard tool for analyzing time-to-event data. Here, the event is machine failure. The Cox model takes the degradation patterns learned by the MGP and relates them to the probability of failure occurring over time.
And it can handle other factors, too.
Yes, that's a key strength. It can incorporate time-varying covariates, things like changing operating conditions or load that might also influence the failure risk. It's finding the rules that link the observed degradation to the failure risk.
Okay, so we have the MGP for degradation and the Cox model for failure probability. How do they work together in this federated setup?
It's a two-stage process, essentially. First, each site, each factory or location with data trains its own joint model locally. So its own MGP learning local degradation and its own Cox model linking that to local failure data.
Okay, local training first.
Then, and this is the crucial privacy part, Only the learned model parameters, the insights, are exchanged between the sites, not the raw data. That stays completely local.
Right. The sensitive stuff stays put.
Exactly. These parameters are aggregated, usually by a central server, to update a global model, which is then sent back to sites for another round of local training. This happens iteratively.
So the global model gets smarter by learning from everyone's experience, but nobody exposes their raw data.
Precisely. And technically, the federated MGP part uses something called stochastic variational inference to handle the maths efficiently across all the sites and deal with uncertainty. The Cox model part also has its own optimization process. Both are designed so the calculations can be done separately at each site.
The paper actually lays out the whole procedure in an algorithm, step by step.
Yes, Algorithm 1 details the whole FedJoint flow.
So how well does it actually work? Let's talk evaluation. They did simulations, right?
They did. Pretty comprehensive ones, too. They created synthetic data covering different scenarios. Scenario 1 had relatively simple parametric degradation, signals things degrading in a predictable way.
Okay.
Scenario 2 used highly nonlinear signals, much more complex and unpredictable, closer to real-world messiness.
And they compared FedJoint to
Several others. A CenJoint model, which is like the ideal baseline where all data is centralized. An InJoint model, where each site just trains independently on its own data, no collaboration. And also a LMM joint, which uses a simpler linear mixed effects model instead of the flexible Gaussian process.
and the results.
Pretty convincing. FedJoint clearly beat the independent and the simpler linear models, especially, as you'd expect, on those tricky nonlinear signals.
That makes sense. The non-parametric MGP really shines there.
Absolutely. And interestingly, FedJoint's performance was often very close to the centralized gold standard model.
Wow. So you get almost the same accuracy as having all the data in one place, but without the privacy breach.
That's the key takeaway, yeah. It shows federated learning can really work for these complex tasks. They also found, unsurprisingly, that more data helps and predictions get better the closer you are to the actual failure event.
Did they test it on real data too?
They did. They used the well-known NASA turbofan engine dataset. It's a standard benchmark for this kind of RUL prediction work.
Oh yes, the CMA-PSS data.
That's the one. They focused on 4 key sensor readings known to be important for engine health. Then they simulated a federated setup, splitting the engine data across 3 hypothetical sites.
And how did FedJoint do there?
Again, really well. Its performance in predicting RUL and failure probabilities was comparable to the centralized model, even though each simulated site only had a fraction of the total data.
That's pretty strong evidence for its practical applicability then.
Definitely. It suggests the approach works even when individual sites might have limited data on their own.
So summing up the key innovations here, what's really new about FedJoint?
I think the biggest thing is extending this kind of sophisticated joint modeling, looking at degradation and failure together into a federated setting. Traditionally, joint models were centralized, and often they assumed simpler parametric forms for degradation. FedJoint makes it non-parametric and federated.
So more realistic modeling and privacy preserving.
Exactly. It provides a genuinely scalable solution for different organizations or units to collaborate on predictive maintenance without having to share their sensitive operational data. That's potentially huge.
It's helpful to put this in context too. Historically, how was RUL prediction done in ML?
Well, early on, you had 2 main camps, sort of. Physics-based models.
Right, needing deep engineering knowledge of how things fail.
Yes, very powerful if you have that knowledge, but maybe not adaptable if something unexpected happens.
And the other camp?
Centralized data-driven models. Machine learning on pooled data, which, as we said, runs into all those data sharing barriers.
So federated learning emerged as a solution to that data centralization problem.
Precisely. It's become super relevant for industries like manufacturing, aerospace, healthcare, anywhere data is sensitive and distributed.
And the joint modeling idea itself, combining degradation and survival analysis.
That's gained traction too, because it just makes sense the 2 are linked. But early joint models often had to simplify things, assuming linear degradation, for instance.
Whereas FedJoint uses Gaussian processes to handle complexity.
Right. Integrating powerful non-parametric tools like GPs into a federated framework is a more recent and significant development. It allows for that realistic modeling of complex wear and tear within the privacy constraints.
Okay, let's move to our novel notions segment. Where could this research lead next? Any potential extensions or new ideas sparked by FedJoint?
Well, one area I find interesting is adaptive personalization within FedJoint.
Okay, what do you mean by that?
So FedJoint creates a good global model using shared knowledge. But what if we could then fine-tune that model slightly for the specifics of each individual site or even each individual machine?
Tailor it more locally after the federated learning.
Exactly. Maybe learn site-specific adjustments or adapt those inducing points based on local data patterns, but still without violating privacy.
Like a fleet of wind turbines. You have a global failure model, but then you adjust it slightly for one specific wind farm's unique weather conditions or turbine model.
Precisely that kind of thing. You could maybe draw on ideas from personalized federated learning or even meta-learning to guide that personalization efficiently, balancing global insights with local specifics.
That's a neat idea. Finding that balance, I was thinking along slightly different lines. What about explainability?
Explainable AI, XAI, integrating that.
Yeah. FedJoint predicts when something might fail. But could we extend it to give hints about why?
Interesting. So not just the prediction, but the reasoning behind it.
Right. Could the local models learn to identify specific patterns in the sensor data that are strong indicators of failure?
And then maybe share those interpretable patterns or explanations instead of just abstract model parameters.
Exactly. So you'd have a federated system that flags potential failures and suggests possible root causes. Imagine spotting a new failure mode across different hospitals' medical devices based on shared interpretable patterns, without ever sharing patient data or device specifics.
That could be incredibly valuable, especially for safety critical systems. You'd get faster diagnostics, maybe more targeted maintenance actions, even across diverse data sets. It connects to the growing field of explainable federated learning.
So definitely some exciting avenues for future work building on this.
Absolutely. But even as it stands, the core contribution of FedJoint is really significant. It offers a very practical, very timely way to do predictive maintenance when your data is spread out and sensitive.
Yeah, that ability to learn collaboratively without centralizing data.
Yeah.
It just unlocks a lot of potential.
You can see it improving reliability, efficiency, safety across loads of different industries.
Definitely. Well, for those of you listening who want to get into the nitty-gritty, the maths, the full experimental setup, the link to the full paper is, as always, available in our show notes. We really encourage you to check it out.
Yeah, explore the methods. Think about how it might apply to problems you're interested in.
Thank you for joining us for this deep dive into FedJoint.
We hope this conversation has given you a useful shortcut to understanding this important research.